In this next video, we're going to be taking a look at how to write the exponential model and then use it to solve. So if we take a look at our first example, we are given the number of TB, or tuberculosis, cases in 1991 and then again in 1996. So we're essentially given two ordered pairs. We're going to use those ordered pairs to substitute into our exponential equation y equals AB to the x power. A is the initial amount. You can solve for the initial amount if you want to think about year 0 being initial, but that doesn't make a whole lot of sense, and that number won't be very easy to use. So we could use the first year of information that we're given, 1991, and call that our initial amount. Then x will represent the number of years after 1991. So that's the way that I'm going to look at it. So our ordered pairs would be 0 for year 0, or the initial amount, or 1991, 28,500. And then the second ordered pair would be for the year 1996, which is 5 years later, and that was 22,840. So what we do is we use those two pieces of information to substitute into our equation. So the yx will be the second coordinate, the amount after time. A is our initial amount, so that'll be the y coordinate or the y-intercept from that 0 coordinate ordered pair. And B is what we're solving for, the rate of growth, or in this case, the rate of decay. So I'm going to substitute 22,840 in for y. My initial amount is 28,500. I don't know my rate of growth or decay, but I do know the 22,840 occurred 5 years after the 28,500 amount. So then we're going to solve this for B. We start by dividing by the 28,500. Again, I recommend not getting a decimal approximation until you absolutely have to. So I'm just going to drop my zeros and write 2284 over 2850. Make sure you only drop 1 0 on each of them if you're doing it this way. Equals b to the 5th. And the way to cancel a 5th power is by taking the 5th root of both sides. So I'm going to take the 5th root of this fraction. Make sure that you use parentheses when you're typing that into your calculator. And this gives you your b value. And I got rounded to the nearest thousandth place, 0.957. So then we write our exponential model, substituting in the a value that we got for the initial amount and the b value we solved for. Y equals 28,500 times our b value, 0.957, to the x power. So there's our model, and now we're going to use the model to predict the number of cases in 2000. So what we're going to do is use the fact that 2000 is 9 years after 1991, and that will be our x value. So we're going to substitute that into our model. And then we can just punch that in on our calculator. And I got, of course, rounded to the nearest case because half a person can't have TB. So I got 19,189 cases, because we always label our answer. All right, so the last one is asking us to find the amount of error in the model. So we're given the actual number of cases, and we know our predicted. So to find the percent error, we take the difference. So we're going to subtract the two amounts. Our difference was 141. You just want to take the bigger number minus the smaller number. It doesn't matter if the difference is over or under. We're just finding the percent error, and then we could say that it was over or under. Divided by the actual amount. So we're not going to divide by the amount that our model predicted. We're going to divide by how many cases there actually were, which was 19,048. And when we divide that, we get about 0.007, which is approximately a 0.7 or a 0.7% error. Make sure when you convert it to a percent, you multiply by 100. So our error was very, very tiny, which means that our model was extremely accurate. For this case, the longer that we predict the model out for, the less accurate it would potentially be. All right, last example. This time we're looking at land that has grown in value. Same thing to set up the model. I am going to start with 1960 as my initial amount, so I'm going to call that year 0. And I'm also going to make the numbers smaller, use my y values in thousands. So year 0 was worth 30,000, and then 2000, of course, is 40 years later, and it was worth 212,000. So when we use those ordered pairs to set up our model, y equals ab to the x. A is your initial amount, so that's our 30. B is the rate of growth or decay. We do not know that value. X will be years later, and y is value after time. So to solve for b, we're going to divide both sides by 30. And we will take the 40th root of 212 over 30. Again, make sure you use parentheses when you're doing this to get your b value. And when you punch that in, you can either do 2 to the 1 over 40 power, or you can find that x root function on your calculator and type in 40, the x root, and then the 212 over 30. So I got for my b value about 1.05. So what that means is that it's growing, which is why it's bigger than 1. We already knew that it was growing, and it's growing at a rate of about 5% per year. That's that 0.05. So writing our model, we get y equals 30 times 1.05 to the x power. All right, next we're going to predict when the value will be 350,000. This time we are given the y value, or the amount after time, and we're going to be solving for x. So because I wrote my initial points in thousands, I'm going to keep that for this one. So it's 350 equals 30 times 1.05 to the x power. Solving for x, I'm going to start by dividing by 30, and I'm going to go ahead and drop those zeros again. And when we are solving for a value in the exponent, we need to use logs to solve. So we're going to start by taking the log of both sides. You can either use the common log or the natural log, or you can undo the curly law if your calculator has that log-based function, and some of the graphing calculators do. I'm going to use the common log, because I think I used natural log last time. And then we can use our log property that when we have a value in the exponent, it can become a coefficient. So I'm going to pull that x out of the exponent. So of course, to solve for x, we're going to divide both sides by log of 1.05. And I got for my x value about 50 years later, which puts us at 2010. Now the question is, does our answer seem reasonable? And then you want to explain why or why not. So you can use some of your knowledge of what happened in our economy in about 2007, 2008, when the housing market really crashed. So the likelihood that this house continued to grow in value over that time is slim to none. So I'm going to say no, due to the recession. Alright, so here are a couple of you-try problems. Please attempt them to the best of your ability and make sure you come to class with questions so we can go over them together.